Oh, hello. Okay, that was really strange. My my window went really small for a moment. Um, yeah, so we'll be starting the Math 2089 uh stats sort of revision seminar in a moment. Um, and sort of just have to set up a few things a bit more. Um, okay. So we might just sort of get started now. So yeah, this is the second half of the Math 2089 workshop. We're going to be going through the stats half today. Now, if you're looking for the numerical methods component, we had that seminar on Tuesday, so you should find a recording for that sort of floating somewhere out on the MathSoc YouTube channel. And yeah, so today we'll be going through the stats half. I'll be presenting just the first two topics kind of briefly, and then Gerald will be presenting sort of our confidence intervals, hypothesis testing, and your analysis of variance. Um, and yeah, sort of, oh, kind of, let me just check that my audio is working properly. Okay. Hopefully that's working well. Um, yeah, okay, so I'll be sort of covering random variables and a bit about sampling. So really focusing on estimators, because that's sort of what gets tested in the finals. But then the bulk of the seminar is sort of going to focus on the latter half, just because, of course, there's a greater focus on topics 3 down to 5 in your sort of final exam. Um, Yeah, so sort of let's get started. So we're gonna just get started with some sort of probability overview, and I'm sure most of us are sort of familiar with this, and we would have studied it in our courses, or um, since this was early in the course, hopefully we're sort of familiar with these ideas. So what is a random variable? So basically, a random variable is just what we get from a random experiment. And more formally, we sort of have this definition here. So it's a real valued function that sort of assigns a value to a random experiment. And sort of just moving on, again, I'm going to be going through this first section sort of really quite quickly, just because there isn't too much of a focus on it in the finals. So yeah, if you do need a bit more help with this front part, we do have a seminar from a few years ago that does go into it in a bit more depth. Personally, I'm going to cover it quite briefly. Okay, so we're going to start off with our cumulative distribution function, our CDF, and that sort of just measures the sort of total probability up to a certain point. So we have this sort of definition here. And we have our sort of properties of our CDF. So we've got this sort of formula over here, which is sort of how we go about measuring the probability of A is less than X is less than or equal to B. So the probability of the interval. Our CDF is non-decreasing, and it sort of moves from 0 to 1. Okay, and then we're going to move on to talking a bit about our discrete random variables versus sort of our continuous random variables. So I think we should also be sort of quite familiar with this. Discrete is sort of our countable variables, whilst our continuous random variables are our sort of uncountable random variables. And the sort of main thing is sort of just the language that we use with it. So with our discrete random variables, we will refer to our sort of probability function as our PMF, so our probability mass function. And meanwhile, with a continuous function, sorry, a continuous random variable, we'll call it our probability density function. And the sort of main thing to sort of keep in mind is when you're dealing with discrete variables, you're going to be doing a lot of sort of summations. And the sort of equivalent version of that in your continuous random variables is when you do integration. So there's sort of, I guess, slight differences between the two. Similarly, you know, when you're dealing with continuous random variables, you would also use differentiation a lot. With your discrete variables, you would sort of opposite summation, so you'll take the difference, I suppose. But yeah, let's sort of move on now into expectation. So what is the expectation of a random variable? Well, it's sort of just a way that we go about measuring the center or the mean of it. And we sort of have this formula over here. So to calculate the expectation in the discrete case, you just take the sum of all of the x multiplied by the probability at the point. And with our continuous random variables, you're just going to take the integral of that instead. And generally speaking, with your expectation, and I think I might actually go into that on the next slide, our expectation is a linear function. So for any sort of constants a and b, we have this result over here. And this sort of result about expectation being linear, let's just change that style, is actually really important, and we'll probably actually go ahead and use that when we're proving a lot of things in the future. Something else that I also wanted to point out, I might have put on a slide later, but I think it sort of fits in nicely here. But generally speaking, when you calculate the expectation of anything, right? So over here, I'm just going to do it for the continuous case. It looks really similar in the discrete case. But let's say instead of just wanting the expectation of our sort of random variable x, if we wanted the expectation of some function of that random variable, let's just call that g of x. So this g of x could look like anything, and that's a capital X over here. You're generally just going to, instead of taking the integral and multiplying by x, you'll just multiply by g of x, f of x. So you sort of get this formula over here instead. And that sort of holds for really any real function g of x. So the one I'm sure you guys are familiar with is if you want the expectation of our variable squared, you'll just multiply it by x squared. Okay, and that's sort of going to play into our next section here, which is sort of talking about the variance. And I do realize that we are going through this section quite fast, but I suppose I'll keep an eye on the time and see if I need to slow down a bit. But yeah, so the variance is sort of the way that we go about measuring the spread of our random variable. And we sort of have this sort of definition over here for our variance. Now, this that I've highlighted is the definition for variance, but the actual formula that you'll use a lot in the computation of variance is actually what we have on the right side here. And this is sort of actually easy enough to prove if you actually go ahead and sort of expand this out and then use the properties of our expectation over here. But this is sort of the formula that we actually use because sort of it's quite easy to actually calculate. And we have a few sort of properties for our variance. So for example, our sort of variance is always going to be greater than 0 or equal to 0, and that's because of all the sort of squaring happening here. And our variance is, unlike our expectation, it's not actually linear. So instead we sort of have this relationship over here. And this sort of third property, the variance of a constant is 0, I guess sort of ties into the second property over here. Yes, so sorry, I'm just checking the stream in case you're seeing like black stuff go over my page. Can't figure out how to get rid of it. Yeah, so let's sort of move on now from variance, and talk a bit more about computing the variance. So as I said, this is the formula that we actually go about using when we calculate our variance, and this is we've just expanded the formula for the discrete and continuous cases, and yeah, so I guess we're just showing you that on this slide. But let's actually just sort of jump into a few example questions. Now, when it comes to the 2018-19 finals, there tends to really be only one or two sort of questions on calculating things like the variance and the expected value. So we're not going to go through it sort of too much, and sort of been why we've been going through this front section so fast. But yeah, let's have a look at this question. So this is from 2019. Let x follow the exponential distribution, and then we have our PDF over here. And the nice thing about these questions is that they will sometimes give you things like the expected value and a sort of non-central moment here. And that saves us from actually having to do a lot of the work ourselves. And so when we have to show that the variance of x is equal to our mu squared here, it's actually really straightforward, right? Because we know that our variance is equal to e of x squared minus our sort of e of x squared. So you really just have to sort of substitute these values into that formula. And yeah, it works out really nicely. So sort of quite a straightforward question there. And we'll sort of continue on with the remaining parts of this question later on when we go on to the section about estimators, because that was sort of the main focus of this question. Let's do another example where we actually have to do a bit of calculations. So this time from our 2018 exam, and we have x following our Bernoulli distribution. And if you guys remember, our Bernoulli distribution is our sort of discrete. It's a discrete distribution. You can kind of see that over here where we've defined our PMF as well. So let's go ahead and calculate our expected value and our variance as well, right? So if we just remember back to the formula of our expected value for discrete, we're just taking the sum of all our sort of points and the probability there. And what that's going to look like for this question is just going to be, 0 times 1 minus pi, and then 1 times pi. And obviously you can kind of do that in your head, but since we need to show, the question like asks us to show the answer, you'll need to write out your sort of whole working out. And we sort of get this, so our expected value is pi, sort of like the question says. And with our variance, we're going to do a very similar thing. So again, with our variance, we're going to first need to find the expected value of x squared. So we'll sort of just go ahead and do that. And again, sort of just showing full working out for it, as sort of tedious as it is. So this time, instead of using x, we're just going to multiply it by x squared. And that's actually going to give us a very similar thing, right? Because we're dealing with x is equal to 0 and 1. I guess we'll sort of just write out the whole thing, plus 1 squared times pi. And again, that's also going to be equal to pi. And then what happens is when we go ahead and compute the variance, we're just going to get pi squared minus pi, which is going to give us that result over here. And I sort of just have this all written out here as well. So, oh, sorry, my mistake. Pi minus pi squared, not pi squared minus pi. Yeah, so we sort of just substitute it here and we get the result that we want. So yeah, calculating our expected value and our variance is quite straightforward. For our discrete cases like this, it's sort of just multiplying a bunch of numbers together. If you get a continuous function instead, let's say we actually had to go ahead and compute our expected value and variance here, what we'll do instead is, of course, just integrate this function over here. All right, let's move on now. So the next thing we have is our standard deviation. And our standard deviation is sort of just simply taking the root of our variance. And the reason we do this is because when we look at like a bunch of data points, when we calculate our variance, and I'll sort of just go back to the formula for it. When we calculate our variance, we're actually going to end up, our units are going to be squared, essentially. So what we sort of want to do with the standard deviation is standardize that. So we want to bring it back to the sort of same units. And that's sort of why we have our standard deviation. Okay, so that's going to sort of wrap up that section. The next part that we're going to move on to is just a small bit on joint distribution functions. Now, as far as I know, these don't really tend to be tested all too heavily in the finals. I kind of struggled actually to find examples of these questions, but we'll still sort of go through the theory behind it. And I've just noticed a few things. Let me just add commas there. But yeah, with our joint distribution function, sometimes we want to measure like the combined sort of probability of both one event, sort of X and Y happening at the same time. And that's sort of where we get our joint distribution functions from. So on the screen here, I sort of just have the definitions for our discrete joint CDFs, but then also our continuous joint sort of cumulative distribution function. So a bit of a mind blank there. And the main thing with our joint distribution functions is we also want to sort of talk about our marginal distribution. So sometimes you are given the sort of joint function. So sometimes you'll be given this guy over here or this guy over here. And you'll be asked to compute the marginal probability. So you want to find out the sort of distribution of only X or Y from the joint distribution. In that case, all you sort of have to do is, in a discrete case, you just have to take the sum of all of the sort of Y to find your sort of distribution, sorry, PMF for X, and sort of the same for finding your distribution for Y. And with your continuous case, to find your distribution for X, you're just integrating with respect to Y. And sort of with Y, you just integrate with respect to X. Okay. So that is our sort of joint distribution function. And sort of one thing that I'll point out now is if you notice over here, I haven't really given a definition for the continuous joint distribution. That's because unlike sort of what we have over here, which is just, you know, the probability of X and Y for a particular X and Y, And that's because with our continuous random variables, the probability at a single point is actually undefined, right? So we can't really write a similar thing. So when we think about our joint distribution function, we really just think about this as the sort of derivative of our joint cumulative distribution function here. And that's generally the case with sort of, if you ever get a question that asks you to find like the PDF of a continuous random variable, most of the time you actually want to start off by finding the CDF first, and then differentiating to get your PDF. So that's sort of just a tip over there for that. And oh yeah, this is where the sort of slide is that I sort of mentioned earlier. And it's just sort of a nice result with our expectation. And earlier I wrote it just for sort of one variable, where I had the expectation of a function. And I'm just going to do in the continuous case. Again, really similar definition for our discrete case. We had this sort of idea here with our expectation. The same thing holds when we have a function of two variables. So you still just sort of multiply by it itself. And of course, in this case, we'll multiply it by that joint PDF or PMF. And the nice thing about our expectation is the sort of the linearity property of it always holds. And sort of when we do a few example questions later, you're going to see that that works really nicely. Yeah, it's a really nice property. Okay, what we're going to move on to now is independent random variables. And this is sort of the really nice and important one to remember. So basically what we have here is two variables, x and y, are said to be independent. And you might have seen this formula for it as well. It's sort of the same thing. But if this probability here is equal to the probability of A, sorry, I should be using x and y, not A and B. The probability of x and the union of y is just equal to the probability of x times the probability of y. And this is sort of what it looks like in the discrete case and in the continuous case when we're looking at our joint, what's it called? Joint distributions as well. And this thing down here in the box is the really nice sort of result that comes out of it. Is that if you take the expectation of sort of two functions of sort of independent random variables, then you can actually just multiply those expectations together. And sort of, I guess more cleanly, that's sort of just saying, well, if x and y are independent, then the expectation of xy is just equal to the expected value of x multiplied by the expected value of y. Yeah, so now we're going to talk a bit about covariance. And what covariance is sort of this formula over here. But what it actually is when we're thinking about sort of these two random variables, x and y, our covariance basically tells us about how these two variables sort of change with each other, so how they vary against one another, if that sort of makes sense. And this is the formula, the actual sort of definition of covariance, this one that I'm highlighting here. But you'll kind of see this thing over here in bold that we've said is very important is what we actually go about using when we calculate covariance. And that's just because it's a lot sort of easier to actually calculate compared to what I've got highlighted up here. We have a few more properties as well for covariance. So for example, our covariance is also symmetric. And we've also got like, the covariance of x and x with itself is just a variance, and bilinearity as well for it. But this one that I've got in the box and in red is sort of just our important one. And sort of one thing to sort of have a look at when we're looking at this formula, and I might just kind of write it up here, is earlier when we talked about independence, we said, well, if x and y are independent, then e of x times y is just equal to the expectation of x times the expectation of y. And what that sort of means is when you calculate the covariance of two independent sort of random variables, we're actually going to wind up with 0 because, the covariance is just going to be e of x e of y minus e of x e of y. So that's going to give us a 0. And one thing sort of important to point out about this is if x and y are independent, then your covariance is always going to be 0, but the opposite isn't always sort of true. So if your covariance is 0, then it doesn't mean that x and y are independent. So that's just something really important to keep in mind, that that's a sort of one-way relationship. And now we're going to sort of we're going to sort of bring where covariance is important. Unfortunately, that was not a coherent sentence. Okay, let's start again. So we're going to talk about why sort of our covariance is important. And that's sort of when we're calculating the variance of a sum of sort of random variables. And this is sort of the result that we get. Yes, that was also the wrong thing. This is the formula that we get when we calculate the variance for x plus y. And the really nice thing about this is earlier we just sort of talked about how if your x and y are independent, then your covariance is going to be 0, right? So if x and y are independent, then we actually get this really nice sort of result here, where we can sort of just add our variances together, of course, with our a squared and our b squared as well. And this is going to be really important in a moment when we sort of go ahead and talk about our random samples and our sort of independent, because independence is sort of going to be an important feature of those. And we're going to be able to use this result down here to sort of prove certain things. Okay, let's just jump into an example question, because I know I've been sort of going through the theory quite fast. So it might sort of be a bit confusing. But this is sort of an example from the 2009 test. And we have this question here. So suppose that x and y are, again, independent. So we know all those nice results that we had earlier, we can use those. And we have that they're also our standard normal variables. So just to note that, and I don't know why that's writing in purple. So our mean is going to be 0 and our sort of variance is going to be 1, right? So what is the distribution of x plus y? And what we sort of know from earlier is that if we have independent sort of, if we have independence, we have, well, first of all, we don't need independence for this, but when we look at our expectation, the expectation of x plus y is just equal to the expectation of x plus the expectation of y, and that just follows from the linearity of the expectation without independence in mind. But then with variance, what we sort of had earlier was that if x and y are independent, then we have this sort of really nice result over here. So we can just add our variances together. And that's sort of what we have to do in this question. So basically, the sum is also going to be normally distributed, and what we will do is we will just simply sort of add our means together, and then also add our variances together. And since they're both standard normal variables, that just gives us our final distribution, which is our normal distribution with parameters sort of 0 and 2. Okay. Yeah, so let's move on now. And we're going to talk a bit about correlation. So there's going to be a bit more about correlation later on in the final section. We're sort of just introducing the idea of the correlation coefficient right now. And that is just sort of basically this formula over here. And the reason we go about calculating our correlation is very similar to why we go about computing our standard sort of deviation, our standard error. And sort of because we're sort of standardizing x and y. So the nice thing about correlation as well is when you sort of see your correlation, you can get a really nice sort of visual picture of how your data might look like. And that's because your correlation is always going to be between negative 1 and 1. And a positive sort of correlation, and you guys may have seen this sort of, I might just make a page. And you'll probably have seen like diagrams like this before, where it's like, oh, if you got data that looks like this, that means we have a positive correlation. And since we have sort of a strong linear relationship here as well, that also means that our correlation is going to be close to 1, right? And then sort of an alternative for that is if we've got a bunch of data points that kind of have like a positive relationship, you can kind of see it. But the relationship is a lot weaker, then our correlation is going to be a lot closer to sort of 0. So the magnitude of it isn't going to be as large. And we sort of get the vice versa for a negative correlation. So if your correlation is negative, you're going to be having a, you're just going to have, your relationship's going to be like this instead. And something like that. Yeah, so that might be sort of like a stronger relationship, or I should get rid of some of these data points. And then likewise for your sort of lower correlation values. Okay, let's move on to talking a bit about sampling distributions and sort of just briefly introducing our central limit theorem. And this is sort of where I would say the finals actually go ahead and test this stuff a bit more. So question 3, okay, because this is combined like with the numericals part, these stats tend to start on question 3. And like one section of question 3 usually tends to test sort of this section. Like this whole sort of section with estimators and all of that. So I guess it's sort of like somewhat easy. You want to be getting these questions correct because they're like the more easier questions in your finals. So yeah, I'll be spending a bit longer on this section. But yeah, so first of all, what is a random sample? And what we have with a random sample is this sort of property here, which is independent and sort of identically distributed. And the sort of whole idea behind that is in stats, of course, we have sort of our population, but it's sort of going to be, and it's usually very hard to actually, measure something for the whole population. So instead, what we do is we go ahead and we take a random sample. But a random sample has to be independent, and it also has to be sort of identically distributed. Otherwise, I suppose the sort of tests that we do with that sample aren't going to be, I guess, the most reflective of the population. So yeah, we need these two things here. So basically, anytime we take a random sort of sample in this course at least, we can assume independence, which is sort of the really nice thing, and sort of why, those nice results with variance that we got earlier are quite important, because we're dealing a lot with independent variables here. Okay, we're gonna quickly go through the central limit theorem. Now, Gerald will probably sort of cover questions to do with the central limit theorem a bit more in his section with confidence intervals and sort of hypothesis testing. What I'm doing here is sort of just introducing it. And the central limit theorem is like, I guess we have it written up here, but it's sort of like the big result in stats. Basically, like, a lot of things use the central limit theorem. And it's also sort of just a really fascinating theorem as well, because what it sort of says is for any random variable, the mean of a large sample is sort of approximately normal. So even if, the original distribution is not a normal distribution, the CLT says that the mean is eventually going to follow a normal distribution, which is a really nice sort of result, because it just allows us to sort of approximate a lot of things to our standard normal distribution. And this is sort of this that I have over here is probably the form of the central limit theorem that you've seen a bit, more often. And just generally speaking, it's a sort of really good idea, I would say, just to memorize the central limit theorem. But yeah, so you'll probably be seeing this a lot more in the confidence interval section and hypothesis testing. So for now, we're just going to introduce it, and then we're sort of going to leave it there. And what I'm going to sort of focus on now is our estimators. And you guys tend to sort of get like, one question at least on estimators. So it's really sort of good to be familiar with what's happening here. And our estimator is basically how we go about sort of estimating the value of like a certain parameter, right? So for example, if we want to go and estimate sort of our mean here, so if we want to go and estimate the mean, we might go about using the sample mean, right? Which is just this guy sort of over here. And in this course, we... Oh, okay. Sorry about that. Give me a moment. Oh, okay. Someone just came to the door, so my dog's gone up in a frenzy. Hopefully we don't hear any more barking, or hopefully you guys didn't hear the barking just then. But yeah, so going on, in this course at least, we don't actually, you guys don't cover sort of different methods of finding various estimators. In all of the sort of questions, you'll just be given the estimator, and then you'll be asked to sort of evaluate certain things about the estimator. And one thing that I'll sort of just point out now is because the estimator is a function of our variables, right? And since it's a function of, all these guys here, and these guys are random variables, then naturally our estimator is also going to be a random variable. So everything that we were sort of doing earlier, we can also do with our estimators. And that's going to sort of play a part when we go into this section, which is the properties of our estimators. And we sort of have three or four sort of properties that we focus a lot on in this course, and they are your sort of bias, efficiency or sort of variance, consistency, and then also your mean squared error. Okay, so let's sort of just go through the definitions of all of these properties. So let's look at bias first. So the bias of the estimator is sort of given by this formula over here. And I guess speaking a bit more like what does this formula actually say? I don't know why that's not turning into a nice rectangle. What is this formula actually calculating? Essentially the bias tells us about how close our sort of estimator is to the true value, right? So this theater over here sort of, I guess, represents the true value of our parameter. And then, of course, the expected value of our estimator is going to give us like the result from the estimator. So that difference is going to be sort of seeing the, I guess, difference between the estimator and the true value. Okay, I think I've made that point enough now. So if the estimator is unbiased, then of course our bias is going to be equal to 0. And we're going to get this result over here, right? So the expected value of the estimator is equal to the actual parameter. And I think in a moment, there's actually a good diagram to sort of show this. But we'll sort of cover the next thing first. Yeah, so we have a bit of an example over here. So this is using the estimators that I had over here, and I might just go ahead and screenshot that and then take that down to this page. So sort of just an example with bias is we can see that our first estimator over here is unbiased, since the expected value of it is just going to give us our theater, right? And that's sort of just assuming that, where is it? Okay. Yeah, sorry. Yeah, so that's sort of, we're just taking the, over here, we're just taking the expected sort of value of x1, and I haven't actually gone ahead and defined the stuff too clearly. But yeah, so basically, we can just sort of have a look at these, and you'll notice that the third estimator over here would actually be biased, because if we sort of just use that linear property of our expected value, we'll end up with 3 on 2 over here. So that's going to give us a biased estimator. And generally with your estimators, you want to, a lower bias is better, right? Because you'll be closer to true value. And the next property that we're going to go into is efficiency. And efficiency is sort of just the word that we use for variance. So a sort of an unbiased estimator should also have a smaller variance, right? So you can have an estimator that has a really sort of no bias, right? So it's an unbiased estimator, but if it has a really large variance, then it still might not be a really good estimator to work with. Yeah, so we also just had the same example as earlier. And we'll sort of go into a bit more of a well-defined example later on. Yeah, so now we're gonna also just move on to also just following on a bit with variance is with consistency. So not only should the variance be small, it should also decrease as the sample size increases. So if you have a sort of variance that is small with a small sample size, but it grows larger as your sample size increases, then that's also not a really good estimator to be working with. So instead, we want that sort of variance to decrease as our sample size increases. And that's sort of where consistency comes in. But the question here is like, okay, well, let's say I have, I'm given a few estimators, right? And I have like, oh, my first estimator here. And this guy over here has, he has, a low bias, but he has, a large variance. So small bias, but, not very efficient. And then we've got a second estimator here, which has got a slightly sort of higher bias. So not like a huge one either, but a larger sort of bias than our first estimator, but it's got a smaller variance. How do we decide sort of which estimator is better? That's where our sort of final property comes in. And our final property is our mean squared error, which is given by this formula over here. And that sort of just combines all of these three properties that we sort of talked about earlier into one formula. And it sort of allows us to evaluate our estimators better when we have, this sort of situation happening. And generally, the smaller your mean squared error, the better your estimator is. Okay. So I guess if you're given two estimators and you're told to calculate the mean square error for both, and the question asks you, oh, which one's the better estimator? It's going to be the one with the smaller mean squared error. And that almost sort of wraps up my section. But before we sort of move on, I just want to go into a more concrete example of basically everything that we've covered up to this point, because I'm aware that I've been moving through the content quite speedily. And that is following off one of those example questions that we did earlier in the variance section. So again, from 2019, we have our exponential distribution. And the whole question section is this, and I might just zoom out so we can see all of it. So this is the whole question. Now, it is like technically parts A down to B, but I couldn't get the numbering to work like that, so I'm just going to refer to them as 1, 2, 3, 4. We already did 1, and this sort of result is going to come back later in some of these questions here. But the main thing with this question is actually looking at our estimators. So we have to show that it is, unbiased. We have to calculate the standard error, and then we also have to check whether this estimator over here, our sample mean, is consistent. So let's go ahead and actually work through all of these questions, and I might just sort of make myself a white page here. Okay, so I'm going to also just drag out a few things. So I'll just write the estimator up here. Okay, so you guys will probably actually be like given this estimator quite a bit because it's sort of a nice one to work with. So this is our estimator. The first thing that we want to do is we want to verify that it's unbiased. And if we sort of think back to our definition of unbiased, it's basically that the expected value of our estimator is just going to be equal to sort of the true value of the parameter that it's estimating. And since this is estimating our mean, essentially we want to just prove that the expected value of this is equal to our mu over here. So I should just write that proof. And the main thing with these questions is you need to make sure when you're showing or like using the properties of linear combinations, you need to make sure that you're justifying each step that you do along the way. So I'll sort of just make sure that I'm doing that as well. Okay, so let's just go ahead and actually show that. So if we want to take the expected value of our sample mean here, we're really just taking the expected value of, and I'll sort of just write it out. Now, this over here is actually just, well, x1 plus x2 all the way up to x of n. So it's just the sum of all our sort of random variables. And then what we know about our expectation is that our expectation is linear. So when we, I guess, see something like, oh, e of x plus y, and I think I've written this earlier, we can actually just add up those expectations. So this actually works out really nicely. And again, when we have a coefficient, right? So for example, e of a of x, we can actually just take out that constant really nicely. And this works really nicely in this proof, right? Because the next thing that we sort of get is that this is then equal to 1 on n outside of e of x1 plus e of x2, the expectation of x2, all the way up to the expectation of xn. And I have not left myself a lot of space on the side. But I guess I can just write it up here. So this follows from our linearity of expectation. So let me just figure out where I can write that somewhere, because you want to make sure that you also sort of just include those results in your answer. Expectation is linear. And then what we sort of know about all of our sort of x1 up to xn is that since this is a sort of random sample, then it's also going to be identically sort of distributed according to our exponential distribution here. And what we know about that is that all our sort of expected values are then going to be equal to mu. So what we wind up getting is that this is equal to 1 on n multiplied by n times our mean. And this sort of just follows from our the fact that they're all identically distributed. Okay, and then if we sort of just go ahead and write the next line, you can go ahead and see that we've proved what we sort of set out to prove. Okay, so that is part 1. Now with part 2, we want to go ahead. Sorry, that is part 2. With part 3, we want to go ahead and calculate the standard error. So this time, we'll start off by finding the variance, and that's because also in part 4, we want to see whether our sample mean is consistent, right? So we're going to need our variance. So let's go ahead and sort of calculate our variance. Oopsies, variance of x bar. Okay, so let's sort of just write that out fully again. So I'm just gonna, I guess, write out that expanded definition for our sample mean. So that's just x1 plus x2 plus da da da, all the way up to xn. Okay, now the question also gives us a really big hint. We want to use the properties of linear combinations, and more specifically, we also want to use that property that all these sort of variables here are independent. And what we know about independent sort of variances is that we can add them. So, and I might sort of just write that out here, right? All we know if x and y are independent is we get this over here, plus b squared variance of y. So we can just go ahead and apply it to this right-hand side over here. And what we're going to wind up with is 1 on n squared, because we're squaring that. Outside all of the sort of variances added up. So then we have variance of xn. And then doing a very sort of similar thing that we did earlier is we know that all of these are identically distributed. So they're all going to have the same variance. And in part 1, we actually showed that the variance was equal to this value over here. So if we just sort of go in and substitute that in, we're going to get our variance is equal to 1 on n squared times, since there's n of these guys here, like that's happening n times, n mu squared. And if we sort of just simplify that, we're going to wind up with this guy over here. And the question also asked us for the standard error. So then all we need to do is, well, our standard error is just going to be equal to the square root of this variance over here, which is just going to be equal to what we got in the question. And the next part is also about whether this estimator is consistent. And if we remember back to the definition of consistency, that was just talking about how as our n increases, our variance should decrease. And if we actually just have a look at this result that we got over here, we can see that, we have n on the denominator here. And what that means is as our sort of n approaches infinity, our variance is actually going to approach 0. So that also means that our estimator is consistent. And one thing that I've actually done kind of a bad job here is I haven't written out my reasonings too clearly. But yeah, you want to just make sure that in your own test, you actually go ahead and write out the reasoning. So like for this one, we were using the independence. And for this one over here, we're using the fact that all of these variables here are identically distributed, so they're going to have the same sort of variance. But yes, that is sort of our estimators and sort of the type of question that you'll be asked to do with your estimators. So what I might do now is we're going to move on to confidence intervals, and Gerald will be presenting that. Okay, so let me just check whether that's good. Good to go. Okay, so I'll be handing over to Joe to present the next sections now.
Hello, can everyone hear me just before we start? We'll start in about a minute. Um, just making sure everything's okay. Okay. Um, I suppose we can get started. If you guys can't hear me, then let me know. And I will try to fix it. So, welcome to the second half of the seminar. We will be covering sort of the more statistical aspects of the course. So we'll start with confidence intervals, which leads naturally into hypothesis testing. And then we'll look at sort of some more and sort of more on more treatment groups. So when you're dealing with hypothesis testing, you'll be normally dealing with two groups. You'll be dealing with a control group, and you'll also be dealing with a treatment group. But in some cases, it might be more treatment groups instead. Large, sufficiently large. Then what you'll end up getting is um, the mean, the distribution of the mean will be approximately normal. And so what you can do is you can standardize this to a normal, standard normal distribution. And then when you get a standard normal distribution, then everything is relatively simple. And so the central limit theorem tells you exactly um, this property here. When you standardize your when you standardize your distribution, then you get that the distribution you get in the end follows or approximately follows a standard normal distribution. Okay. Now, since you know that level of confidence that it contains the true mean. So if we look at the true mean being mu, and instead of finding what this actual mu is, we know that we can sample um, we can take random a bunch of samples from a population. Then we want to determine sort of an interval where we obtain some information about the location of the mean, of the true mean. And so what we can do is we can actually build up this interval that tells us with some level of confidence whether or not the interval that we have contains the true mean. So what we can do is we can sort of start by looking at uh, the probability that we want Z to be, sort of centered around our points. So we say, okay, well, if I know that the probability that I want the true mean to lie inside of my interval to be 1 minus alpha, where alpha, remember that alpha is always between 0 and 1, then we can say with some probability that if I consider this interval, then I will contain a true mean, right? Because if you consider exactly this statement here, and you just solve for mu, then you know that within this interval, you will contain mu with some level of confidence. And this is exactly what the so this is exactly what the confidence interval really tells you. It tells you some location or some interval where the true mean will lie. And we do this with some level of confidence as well. Okay. So what we can say then is the interval that we're considering, the confidence interval, with this percentage level of confidence, really becomes this interval here, right? Because from the previous part that we saw that it was x bar minus z1 minus alpha 2, sigma over square root of n was less than equal to mu, which was less than equal to x bar plus z1 minus alpha over 2 times sigma divided by the square root of n. Right? And so this is really my interval that I consider. And I know that with, alpha level of confidence, I know that this contains my, okay. But what you'll see here is there's a bit of a problem because oftentimes we are actually not given this value for sigma, right? Like oftentimes when you look at a population, you're not actually given what the actual standard deviation is. And so you can't actually create this interval here because, well, you don't know your standard deviation, you don't know your variance, you don't know the true variance. So what we need to do then is we need to think about somehow finding a way to estimate uh, sigma. We need to somehow estimate the standard deviation. And this is exactly what we did in the previous topic when we started looking at estimators. In particular, what we can do is we can actually estimate sigma. We can actually estimate sigma with what we call a sample variance or a sample standard deviation, right? Because in practice, the sample standard deviation is much easier to obtain because you're just sampling from a population, you're sampling from some group of people, and you just calculate you calculate the total variance or you calculate the total standard deviation, it's much easier. And if you sample it well enough, this might tell you a lot about the actual population. Of course, it doesn't tell you the full information about the population, but you can infer some characteristics of the population using the sample standard deviation. And so the sample standard deviation is a very useful estimator when we don't actually know what our true standard deviation is. And this is exactly what we're going to do. So really, all we want to do is we want to figure out a way to estimate sigma. We want to be able to estimate um, or provide a good estimation for sigma. And so what we can do is we can actually just use the sample variance. And then once we know the sample variance, then we know the sample standard deviation, right? Because once we know s squared, then we just take the square root of s squared, and that will give us s, right? And the natural estimator for the variance is really the sample variance given by this expression here, right? Um, So you're taking the sum over all of your uh, or samples. So you're sampling x1 up to xn. So you're interviewing n people. You take the information and then you basically plug that into the variance, right? This is essentially just the variance um, of n bar. Oh well, yeah, it's just the variance, and then you're dividing by um, n minus one. And that will give you the sample variance. And once you know the sample variance, then you know your sample standard deviation. And once you know your sample standard deviation, then you can use that as your estimator. So one thing we could do is to just substitute sigma for it for us. So instead of having all of these sigma things, we replace it with s. But the issue here is that this is not necessarily normally distributed anymore. So the important part here is this is not normally distributed, which is a problem because in the previous part, in our previous um, confidence interval, this was normally distributed because of CRT. However, this is no longer normally distributed. So we need to introduce another um, distribution that might model the normal distribution more closely. And so this is exactly what the student t-distribution really says. So the student t-distribution really says that, well, you need to give it some degree of freedom. The degree of freedom will tell you sort of some information about the number of people that you model. And it's given by this probability density function. You're not really expected to memorize it. I don't think it will be, well, they might give it to you in some formula sheet and say, just use this. You might be expected to know how to understand this, but you're not expected to memorize this. At least I don't believe. But we just say that a random variable t is said to follow the t distribution with new degrees of freedom, or we can model it as t follows t nu if its probability density function is given by this formula here. And one thing we can notice is that the expectation of t, the expectation is 0, and the variance of t is nu divided by nu minus 2. So one thing that might pop out to you is that this expectation here doesn't depend on nu at all. So this actually means that for any degree of freedom that you decide to give it, the t distribution is actually centered around 0 for every value for nu, right? So in other words, what it will really look like, it might look something like this. It might have high variance, or it might have low variance, uh, or something in between. But what you'll notice is that it will always follow this sort of curvature here, and it will always be centered around 0. This works for any degree of freedom as well, which is very convenient, which is very useful, um, and it's just really nice to have. The variance of t does depend on nu though. So it's nu divided by nu minus 2. Good. Okay. So what we can see here is that because the expectation of t, because the expectation of this student t distribution is 0 for any value for nu, it is indeed symmetric around 0. And so what we have is a really nice expression. We have that t given a new degree of freedom um, of 1 minus alpha is actually equal to minus t nu alpha. Um, that's just something that you might want to keep in mind when you're solving problems, but that's just something that's very useful to have. And so what we can have is, well, what we have is that this distribution here, where instead of having remember that your sigma is replaced with s, where s is your sample standard deviation, actually follows a Tn minus 1 distribution. So here, nu is equal to n minus 1. And we know that t is sampled from n random variables. Right, so your degree of freedom is reduced by 1 from the number of random variables that you have. And then if we use the same procedure where we start with CLT, and we know that if we want to solve for mu, because we want to see what sort of interval gives us ensures that mu is inside of my interval, then we can just approach it exactly the same and we get effectively the same looking formula. The only difference here is that S replaces the sigma. And you're no longer looking at quantiles along a normal distribution, you're looking at quantiles along the t-distribution. And so in summary, if we know that the population is normal, then we just want to figure out whether or not sigma is known. If it is known, then we use the normal distribution. So this is your normal distribution. If it is not known, then we sample it using the sample standard deviation. So we use the t-distribution instead. If, on the other hand, the population is not normal, so if you look at a quantile plot, if you look at a QQ plot, uh, okay, I think I'm back. I think I dropped off for a bit. Um, okay, cool. So let's sort of rewind a little bit then. So let's think about, so if your population was not normal, we can still sample it from a normal distribution, but instead of using um, the actual standard deviation, what we can do is we can just use S instead. So it's just sort of mixing these two things a little bit. Okay. We're going to have a look at the confidence interval for populations. And then once we look at the confidence interval for populations, we're going to go through some problems. Okay. So now previously we've looked at the confidence interval for sort of looking at means or the average. Now we're going to look at proportions. So suppose you sample X from some Bernoulli distribution. So remember that a Bernoulli distribution is your standard discrete random variable. And say that we have n random samples from a Bernoulli distribution. Um, we can define sort of the proportion of individuals that you care about to be the sum over all of your Bernoulli random samples, where we sort of define the Bernoulli distribution really as the following. So one uh, and zero. So I guess like you have some sort of criteria here, but what we can do is we can say the Bernoulli distribution is equal to one if you obtain some value, and it's zero otherwise. And what we can see here is that if you really only care about the people that return one, then the proportion is just the ratio of individuals over the entire sample. And so because you sample n people, then your denominator will be n, and your value for y would be the number of people you care. Right. So um, this is a way to model uh, proportions. So we can sort of estimate proportions using an estimator called the sample proportion. And we know that because y is binomially distributed, because it's a sum of Bernoulli distribution, a sum of Bernoulli random variables, um, then we have that the expectation of y is equal to n times pi, because remember that if you take the binomial distribution with parameters np, then you know that the expectation of x is np, and you know that the variance of x is np times 1 minus p. So if you know that y comes from binomial distribution with parameters n and pi in this case, then you know that the expectation of y is n times pi, and the variance of y is n pi times 1 minus pi. And remember that we define p hat to be y divided by n. So if you use your properties of expectations and variances, knowing that y comes from x1. Okay, hopefully it's better now. Um, Let me know if I drop off again. I should be okay now, I hope. Okay, so let's rewind a little bit. So let's go back to um, some more statistics. So remember that the p hat was y divided by n. And so if p hat was equal to y divided by n, then the expectation of p hat is 1 over n times the expectation of y. But we know the expectation of y is n times pi. So you overall get it's equal. And we can do, okay. And so what you get here is that the variance of your estimator is pi times 1 minus pi divided by n, and the standard deviation is just the square root. And we can see that if we apply the central limit theorem, if we apply the central limit theorem on this, then we get that this approaches a normal standard normal distribution, and we also get the confidence interval exactly the same as what we did in the case where we had means instead. And in this case, remember that if pi is not known, so if your estimator is not known, we can always estimate it using p hat instead. Cool. Awesome. Okay, so let's have a look at an example to kind of hopefully make things a little bit more concrete. So in August of this year, Roy Morgan Research published a poll on rugby viewership of New Zealanders. The poll of 6,422 randomly selected New Zealanders found that 43.6% of them watch rugby on the television. We want to find a 95% confidence interval for the true proportion of New Zealanders who watch rugby on the television. Okay, so let's sort of take a step back a little bit and kind of think about the information that we have here. So the first thing we know is 6,422 is the total number of people that are randomly selected. So this is the value for n. And we know that 43.6% of them watch rugby. So the proportion of people who watch rugby is 43.6%. So we know that if we go here, so what we know here is n was equal to 6,422. And we know that the proportion of people who watch rugby is 43.6%. Why is it still very choppy? Hmm. Okay. It doesn't. Okay, I see the problem. It doesn't find my. Okay, that's fine. I will go back to here. Okay. Okay. Let's sort of restart. Apparently, the whiteboard doesn't work, so I will get back to this. So Here, what we can see here is n was equal to 6,422. And we found that the proportion of people who um, watch rugby is exactly equal to 43.6%. Right, so that means you know that p hat is 0.436. Okay, so since you know that the true proportion is not known, what we can do is we can just use p hat instead. So the confidence interval that you get in the end is, remember that it was, write out the formula first, and then, so it's p hat minus 1.9, oops, minus, um, so here, remember that we need to figure out whether we're using a t distribution or whether we're using a z distribution, a normal distribution, and that's square root of p hat times 1 minus p hat divided by n, and then 0. So p hat plus. So here in this case, you're using a normal distribution. So what we can do here is just write z1 minus alpha on 2, z1 minus alpha on 2 times the square root of p hat times 1 minus p hat divided by n. So this is, remember that, the confidence interval that we get. And then if we just plug everything in, so here remember that we're looking at a 95% confidence interval. So that means your alpha is actually 0.05, right? Because um, remember that we're always taking 100 times 1 minus alpha. And so that means you know that alpha is 0.05. So when you plug everything in, then you get p hat minus z of, well, 1 minus 0.025, which is 0.975 times the square root of p hat 1 minus p hat divided by n. And you can do the same thing. And then you can just plug everything into MATLAB, or you'll probably be given um, a list of commands, and you can just read it off. But generally, this is a well-known result. That's 1.96. Cool. And you get this. So remember that this was p hat. This was your z of 0.975. This was your square root of p hat 1 minus p hat divided by n. And exactly the same here. Okay, let's have a look at another problem. So in a 2011 score, you have, out of 386 responses, 118 indicated a lack of cycling infrastructure as their reason. You want to find, so the first part is to find a 95% confidence interval for the true proportion pi of Australians who do not ride a bike due to lack of cycling infrastructure. So here, you just need to locate what your p hat is. You need to locate what your n is. So when you read this, you're like, okay, well, out of 396 people, that tells you that this is the value for n. And similarly, you know that 118 people indicated a lack of cycling infrastructure. So that means you know that the proportion of people who do not ride a bike uh, because of a lack of cycling infrastructure is 118 divided by 386. So in this problem, you're not actually given the percentage of people, but rather you're given your n and you're given a number of people that you care about. In the previous case, you're given the percentage of people. Here, you're given the ratio. Okay. And once you figure this out, then you sort of know to just plug and chug. So if you have a 95% confidence interval, then it's 100 minus alpha equals to 95. And you solve for alpha basically. So 100 minus 100 alpha equals to 95. So that means you know that alpha is 0.0. Well, in this case, alpha is 5. Alpha is actually 5. Well, 0.05. Yeah. Um, cool. And so you just plug everything into the formula, and then you're basically done. So that was part one. For part two, you want to state two conditions under which the above interval is a valid confidence interval. So this is something that I didn't really cover in the previous slide. But really, what's happening is that because you're employing the central limit theorem, there are sort of two main things that you want to consider. So the first thing is for the central limit theorem to actually be valid, the first thing you need is n to be sufficiently large. Right? Because remember that you're not actually sampling from a normal distribution, you're sampling from a binomial distribution. So you need to have n large enough so that, you know, it's more or less a normal distribution. But moreover, the more important one that you want to consider for the proportion is the empirical rule. Well, you need to check that n times your proportion times 1 minus the proportion is at least 5. And you can just quickly check that this works out. Cool. And so we see that we obtain this. So you can see that this was your p hat, and then this one was your square root p hat 1 minus p hat divided by n. And you do the same thing, but this time you have a plus. For the second part, you just need to check this empirical rule. And this empirical rule really does say enough to suggest that n is also large. Cool. So this was basically the overarching idea with confidence intervals, are really constructing two endpoints so that with enough confidence, why is this? Okay, I think I'm back. Okay. So okay, I don't know how much of that was missed, but the idea with hypothesis testing is, so to kind of just backtrack a little bit, with hypothesis testing, we really assess the accuracy of one hypothesis over another. And one forethought that we want to keep in mind is that we never truly validate one hypothesis. We only find enough evidence that pushes us to one hypothesis over another. So remember that under the null hypothesis, we always assume that it's true. We make the assumption that this is true. And then we basically find evidence for or against the null hypothesis. Generally, we try to find evidence against the null hypothesis. And if we find compelling evidence against the null hypothesis, then we know that we have enough evidence to suggest that we reject the null hypothesis. On the other hand, though, if we don't find enough evidence to suggest anything against the null hypothesis, then we fail to reject. We don't actually accept it. We just fail to reject. Okay, so that's just something to keep in mind whenever you're dealing with statistical inference. Okay. So with the alternative hypothesis, the null hypothesis is really the hypothesis that we assume to be true by default, right? Um, and there are sort of two options that we have with the null hypothesis. We will either reject it because we have enough evidence to suggest that it is less plausible over the alternative, or we fail to reject the null hypothesis because we have compelling evidence against the null hypothesis. Um, with the null hypothesis, though, we often define this to be H0, and the alternative hypothesis, we typically denote this as HA, A being the alternative hypothesis. And then so before we actually get into the hypothesis testing, we want to look at sort of two versions of the hypothesis test. So the first one is the one-sided hypothesis test. So in the case where this is the wrong way around. This is two-sided. This is one-sided. Okay. So in the case where only one extreme is enough, then we call this a one-sided hypothesis test, right? And you can see here the alternative hypothesis is denoted like this, where we only look at one extreme, we don't look at both of the extremes. On the other hand, we have a two-sided hypothesis test, where we have to look at both extremes. So if you look at really what's happening here, if you're looking at the test distribution, then we need to look at both of these extremes here. This is for a two-sided test, whereas if we only care about one side, then we only look at either this one or look at this way here. Cool. And then once we figure out the test distribution, the test statistic, then we can start dealing with the actual hypothesis test. So there's a couple of things we need to keep in mind whenever we're dealing with the hypothesis testing. So if we know that our standard deviation is known, then we typically use the normal distribution because we know information about that normal distribution. If we don't know the standard deviation, then we use a normal random sample, and so we use a t-distribution. And then if we are sampling from a proportion, then we use the normal distribution, right? Because remember that p hat comes from a binomial distribution. And then we can model a binomial distribution with the normal distribution itself. Okay. The next thing we want to look at, once we figure out the test statistic, we want to look at a way to conclude, or a way to talk about the evidence that we gather. So there are sort of two ways to think about the p-value. So the p-value itself tells us how much evidence there is against H0 in favor of the alternative hypothesis. So it tells us um, how unlikely it is for the null hypothesis to be true. So remember that whenever we're dealing with the hypothesis testing, we're always assuming that it's true to begin with. And then once we know that we assume that it's true, then we do our statistical inference, and then we get to a point where we're like, okay, the probability that this happens, assuming that, this is true. So assuming that, my test or my null hypothesis is true, I do some test statistic and then I obtain some value. If the value is really, really small, that means there is really no evidence, or there is really no evidence to support the null hypothesis over the alternative. If it's really big, then that means we have a high probability that the null hypothesis is true. And so what you can see here is the smaller the p-value, the more evidence against the null hypothesis, right? And if there's enough evidence against H0, then we typically reject the null hypothesis. And this is typically the way that we deal with a lot of these um, statistical inferences. Okay. And there's also a two-sided p-value version as well. Um, this should be, so this should be, it's not equal to, let me see here. Okay. So this, okay. Give me a second. I need to really quickly. Uh, uh, okay. All right, let's return. So we're going to basically set up the hypothesis testing now. So the null and so the first thing we normally do is to state what we're actually testing. So we state the null hypothesis and we say the alternative hypothesis. We figure out what test statistic to use. So here, are we using um, the normal distribution? Are we using the t-distribution? Are we using some other distribution that we will look at later as well? And we look at the null distribution, so the distribution of H0, and then we draw a conclusion based on the corresponding p-value or rejection region, which we haven't covered yet. Okay. And really, at the end of the day, what we're doing is we want to determine if H0 was a lie. We don't really determine if it's a lie, but rather, do we think it is more plausible over the alternative hypothesis? Okay. Um, so whenever we're talking about the test statistic, there are sort of three things that we want to consider. So if you know that the standard deviation is known, then we typically use the normal distribution. So this is your normal distribution. Oops. Normal distribution. And if you use the normal distribution, these are your rejection regions. So these are the regions in which if you know that, X bar lies inside this region, then you reject the null, or if X bar does not lie in this region, then you reject the null hypothesis. So you reject H0 if you know that X bar does not lie in this region, or if you know that X bar is less than this value, or if X bar is greater than this value. And really what we're saying here is, does it lie inside of our extreme points, right? So if you consider the extreme point, in the case where you have this um, rejection region being two-sided, we're basically saying, does it lie strictly inside of one of these regions? For the case where you have one-sided, we're saying, does it lie in the extreme region? Because if we know that it lies inside the extreme region, then it's very unlikely for it to happen. It's very unlikely for the, um, well, it's very unlikely that the null distribution is accurate or is more believable than the alternative hypothesis. Okay. In the case where sigma is not known, um, we use a t-distribution instead. So we're using a t-distribution and we follow exactly the same thing. So in the case where we have one-sided, we want to only look at one extreme point or one extreme case. And if we know that we have a two-sided um, hypothesis test, then we look at the case where it falls inside one of the two extreme regions. And in the case where we have a hypothesis test about the proportion, we basically perform exactly the same thing. This time, remember that this follows a normal distribution. Cool. Okay, let's have a look at an example. So this comes from the 2018 paper. So assume Rugby New Zealand want to be able to demonstrate that rugby viewership is in excess of 40% of New Zealanders using a sample size of n. So just an arbitrary value for n. We want to state what the appropriate null and alternative hypotheses for the test are. We want to state what the distribution of the sample proportion is if the null distribution is true. And we want to show that the relevant hypothesis at the 0.05 significance level, the rejection region for p hat can be expressed as this region. Okay, so we can see that we want to determine something about the excess of 40%. So we know that we're going to be dealing with a one-sided hypothesis test because we only care about what happens at one extreme point, right? We don't care about what happens smaller than 40%. So this gives us a very natural way of describing the null and alternative hypotheses. So for the null hypothesis, we're going to say, well, the proportion is equal to 0.4. The proportions is equal to 0.4. And we want to find compelling evidence for the fact that it is in excess of 40%. So the proportion is greater than 0.4. And this is exactly what we get here. Cool. Okay, let's have a look. What is the distribution of the sample proportion p hat if the null distribution is true? So remember that we're dealing with a proportion. So when we're dealing with a proportion, we're going to be dealing with a normal distribution. So we're going to be dealing with a normal distribution. So this is going to be a normal distribution. So what we need to figure out is what the parameters of my normal distribution are going to be. So if we think about the way that it works, if we think back to uh, how we established this confidence interval, we noted that this expression here was it follows a standard normal distribution, right? So if we want to be able to somehow predict what pi is, because we want to find a distribution for pi, then what we want to do is we want to figure out what the corresponding expectation and what the corresponding variances are. But we've already computed that exactly here. So we computed that here, and we computed that here. So so in this course, we will be dealing with the expectation and the standard deviation. Those are going to be the parameters of my normal distribution. So this will give me exactly this. This is my p hat. This is my square root of p hat 1 minus p hat divided by n. And then lastly, we want to show that for the relevant hypothesis at the 0.05 significance level, the rejection region for p hat can be expressed as this. Okay, so remember that we're dealing with a one-sided test, right? Because of my hypothesis. So if I look at this, I'm only dealing with a one-sided test. So we know that we're dealing with an upper bound. So we know that at the very least, we're going to get something like p hat has to be greater than some quantity here. Now, if we look back at our expression for the rejection region, we can see that it has to be greater than pi 0 plus z of 1 minus alpha times whatever this quantity is. So all we need to figure out is what this is, what this is, and what this is. But luckily for us, we know pi 0 is just the null, well, it is the value at the null distribution. And z of 1 minus alpha is something that we can compute. So we know everything that we want here. So we can see that the first thing we want to do is to notice that this is indeed a one-sided test. So that's an important part. We know that the value for the value that we're after is 0.05. So that's my alpha value. And so what we want to do is we require that z is greater than z of 1 minus 0.05 or this value here. And so if you plug everything into your formula, then you get exactly this. And this will be the lower bound for your rejection region, right? Because this was your p hat, this is z of 1 minus alpha, and then this quantity was your square root. P hat 1 minus p hat divided by n. Okay. Now we'll have a look at another example. So this one comes from, I believe, the 2017 paper. Silicon germanium alloys have been used in certain types of solar cells. The paper silicon germanium films deposited by low frequency plasma enhanced chemical vapor deposition reported on a study of various structural and electrical properties. Consider the accompanying data on X equals to the germanium concentration in solid phase, ranging from 0 to 1. Germanium is an abbreviation for germanium, and Y is the Fermi level position. We're given a bunch of data here. The following summary statistics were obtained for the germanium concentration solid phase. And we're given these two quantities here. And we're given that the linear regression model is given by this quantity here. Cool. Okay. We are also given the following output from MATLAB, and we can use these following output from MATLAB to answer the questions. So the first thing we might want to do is to sort of analyze this MATLAB response. This might help with figuring out what to do with the MATLAB response. So let's think about the linear regression model that we have here. So remember that the linear regression model says beta 0 is the value for the intercept, and then beta 1 is the value for the slope. So the intercept is beta 0, beta 1 is your slope. Okay, let's keep going. Okay, so we know that on the row where we have intercept, this corresponds to the beta 0 term. X here refers to the beta 1 term. Okay, so that's something that might be helpful to keep in mind. And we're given a bunch of T inverse commands, so we're thinking maybe the distribution we're going to use is a T distribution. We're given p-values, we're given the T statistic, and we're given the standard error as well. Yeah. We want to perform a hypothesis test to determine whether the variable x is significant in this model at the 5% level of significance. Okay. So here's a couple of things you want to keep in mind whenever you're thinking about the hypothesis test. So if you want to determine whether the variable x is significant in this model, remember that it's y equals to beta 0 plus beta 1 x plus epsilon. Then what you're really after, the thing that you're really interested in is whether or not beta 1 plays a significant role in the actual computation, right? Because if we know that beta 1 is not that relevant, then you know that y is really independent of x. But if you know that y varies greatly depending on beta 1, then you know that there's going to be a type um, of relationship between y and x. Okay. So the natural thing to think about then is, well, my hypothesis test is going to determine whether or not beta 1 is actually significant. So H0 says, um, okay, I don't really care about the beta 1 term, so beta 1 should be 0. And then HA says, no, beta 1 is actually very important because that allows us to suggest that x is actually very significant in this model. So beta 1 is not 0. And so doing it this way, this gives us a hypothesis test, right? It gives us a hypothesis test, and we need to figure out, well, the the two extreme points. So the next thing we want to do is to figure out what the test statistic is, and we want to figure out some other points as well. So I'll probably just so the first thing we want to do is to determine whether x has an effect on y. To do this, we should compare, well, x with the absence of x. This gives us the natural hypotheses, beta is equal to 0 versus beta 1 is not equal to 0, and this gives us our two hypotheses here. We need to figure out what the test statistic is. Well, if we look back at the sample that we're given, we are given 13 samples. So n minus 1. So in this case, remember that n minus 1 is equal to 12. But then we also lose one extra degree of freedom because of this beta 1 term disappearing. So we lose one extra freedom due to our hypotheses. So therefore, our new value is going to be 11. So the degree of freedom that we have is 11, not 12. Um, Finally, we are testing it at the 5% level of significance, and this is also a two-sided test, and so therefore we need this value here. So the first point here is that this is the degree of freedom, this is the value for nu, and then because we're doing a two-sided test, it's 1 minus alpha divided by 2 instead of 1 minus alpha. Okay. So that's equal to this component here. So if we look at beta 1, it's exactly equal to this point here. That's very cool. And so we just need to figure out what this is. Well, we've already figured that out. That was 2.201. This was 2.201. And we noticed that beta 1 was 0, right? Because we're always assuming that the null distribution or the null hypothesis is true. And so we obtain this result here, which is exactly equal to this. So we can see that we reject H0 if beta 1 does not belong in this interval here. Yeah. And we also compute the p-value, which is equal to this. Uh, so the conclusion here is to reject H0. So the GE concentration is significantly associated with the Fermi level position. So that's the conclusion that we make um, out of our test statistic. Cool. So that's basically the idea of hypothesis testing. Now we're going to look at analysis of variance. This is the last topic for the seminar. It's one that pops up quite a lot in your exams, just because we're modeling a random variable using uh, a straight line, right? So we use x as sort of like the x value, and then y is the y value. So we're going to model it with an intercept. So this is called your intercept, and this is called your slope. Whenever we're dealing with linear regression, is that okay. So one thing we always assume is that this error term is pretty unique in that we always assume that the expectation of the error term is equal to 0. So the expectation of the error term is equal to 0, and we know that the variance of epsilon is sigma squared. That's usually something that we always assume. Okay, so the next thing we want to think about is sort of the least square estimators. So typically, in most fashions, we don't typically know the true values of beta 0 and beta 1. Instead, what we can do is just to estimate it. And the best way to estimate it is using the sum of squares. So we use these two um, expressions, and we find that beta 1, an estimator for beta 1 is just the sum of squares of xy divided by the sum of x squared. And beta 0, once you sub it into the formula, you get y hat minus, remember this is beta 1 hat and x bar. So remember that y was equal to beta 0 plus beta 1 x. So we get that beta 0 is y minus beta 1. Oh, beta 1 x. And so if we are estimating beta 0, what we can do is we can just look at the mean of y minus the estimator that we use for beta 1 times x bar as well. Okay. Yeah, so all of the error terms have the same variance, and each error term is drawn independently of one another. You don't really need to. Okay, we can go back live. So remember that we sort of have a linear relationship between x and y. Remember that we are trying to fit y as a linear relationship with x. So there has to be some sort of linear relationship between x and y, and the absolute value of r tells you the strength of the relationship and whether or not it is positive or negative, depending on the sign. Okay. Cool. Okay, so now we're going to actually talk about ANOVA analysis of variance. So with analysis of variance, typically what we are going to see is that oftentimes we want to deal with more than two groups. And so we want to make an inference about, you know, having more than two groups, maybe having three treatment groups instead. Um, in the tip-ins and hypothesis testing that we've done before, that wasn't really possible. We always have inferences about two groups. Analysis of variance tells us something about the inference of three groups, or three or more groups. So the ANOVA model sort of says, okay, you have a bunch of treatments. So mu I, so mu I is, it talks about the mean of the ith treatment, so the ith treatment group, and you're going to have some error term when you are comparing it with um, some other group. So xij is just talking about how two groups are related to each other. So you have the mean of the ith treatment group, and you have some error term related to the jth treatment group. Typically, what we like to do is to model this with a table so we can tabulate the results. So one thing we can see is that the number of treatments or the degree of freedom of the treatment is the number of treatment groups minus one. And the degree of freedom of the error term is n. The case cancel, so we're left with n minus one. Um, squared, so the treatment mean squared, and we have the error mean squared as well. And this is typically just, so you can kind of think of this as the sum of squares divided by the degree of freedom. So mean squared is just sum of squares divided by the degree of freedom. And then finally, we get the thing that we were after, which is the observed test statistic, which is your Fisher distribution. So that's just your treatment mean squared divided by the error mean squared. So once you know all of these terms, once you know everything here, then you know what your Fisher. Cool. So let's have a look at a few examples. So we have so we have three treatment groups here. So we have early, evening, and late. We're given some information about the averages or the means, and we know something about the um, standard deviation. Okay. Um, so some key values that we want to keep in mind is that the value of k is equal to 3. Oop. The value of k equals to 3 because we have three treatment groups. And we have 24 observations, right? We have 8 observations per group. So altogether we have 24 observations. Okay, so the first thing we want to do is to complete the table by determining the missing values. So let's think about this. So number one, remember that was, well, if you want to find the degree of freedom of the treatment, that's just k minus 1. So remember that k was 3, which means that this would be 2. To find 2, remember that this was just the sum of the degree of freedom of the treatment and the sum of the degree of the error. So that's just 2 plus 21. Um, okay. Okay. Um, for the ANOVA test itself, you typically just use the test statistic. So the test statistic is the treatment mean square divided by the error mean square. So a very simple formula here. Um, Notice that the Fisher distribution has parameters d1. We'll see here is of this form here. So you'll have a Fisher distribution with two parameters, one being k, the first one being k minus 1, the second one being n minus k. And then you're going to look at it with 1 minus alpha as your final sort of, yeah. So you'll typically see it as f of k minus 1, n minus k. That's your Fisher distribution. And then you're looking at it over 1 minus alpha. And we reject it if we know that the observed test statistic, so this was f, is greater than this value here. Okay, so let's have a look at, so let's sort of follow on from the previous problem. So remember that this was the original problem. We've just filled out all of the numbers so that you don't have to. And we will now perform an ANOVA test using a significance level of alpha equals to 0.05. So as with every ANOVA test, you just need to figure out what your null and alternative hypotheses are. So the null hypothesis is that all of the means are the same. So in this case, you have three groups. So H0 is that mu1 equals to mu2 equals to mu3. And then HA is always the same. Not all means are the same. Okay. Once you have that, then you just need to figure out. So here, the good thing is that we've already figured out our test statistic, that's 20.72. So what we want to do now is just to figure out the last part. So we have that f is I think we have that. Wait. Yes. So we're also given this expression. We're also given this table here. So remember that we want to figure out f of k minus 1, n minus k, and 1 minus alpha. Remember that alpha was 0.05. So in this case, we're looking at f of k minus 1, n minus k at the 0.95 level. Okay, so you look at this and you're like, okay, well, I'm looking at a Fisher distribution, so I can cross off a lot of these. Cross this off, I can cross this off, I can cross this off, cross this off, I can cross this off. Um, and I can see that I only care about the 0.95 parts here. Okay. So now K was equal to 3. There are 3 treatment groups. So this immediately rules this one out. So we don't care about this one. And is 3.467. And so all you're really checking is if you obtain this result here, and then your conclusion is that you want to reject H0, and there is strong compelling evidence against it. Okay. Okay, so just before we end off, we will also look at some sort of important details about the ANOVA test. So the ANOVA test really only tells us that not all of the means are the same if the null hypothesis is to be rejected. However, it doesn't tell us anything more. It only tells us that at least 2 of them are different, but it doesn't tell us exactly which ones. One way to kind of go around this, one way to figure out which pairs of treatment groups have different means is to do pairwise comparisons. Right? So we can look at all of the pairwise, but this is pretty problematic because remember that the confidence interval really only asserts us that 0 doesn't belong in this region with alpha percent probability, right? Because we are always alpha percent sure that it is inside this interval, it's not inside this interval. So we can go ahead and compute confidence intervals, which is given here. I'm not going to go through why this is the confidence interval, but you can just memorize this. Just memorize this expression here. Um, so for any 2 treatment groups, I and J, we can compute the confidence interval as this expression here. Remember that this is your t distribution. And this is your error mean squared. Ni and Nj are the number of observations. So number of observations in group I and group J. Okay, so let's have a look at how we might go about doing this. So I'm not going to actually write out all of the values, but you can kind of see that we had 8 things inside group 1, 8 things inside group 2, 8 things inside group 3. So I've just sort of highlighted it all here. You can go ahead and check that yourself. But remember that we had to compute a 90% confidence interval on the difference between the true downloading times in the evening and late night. So we're looking at qualities really the same. Are they equal to each other? Are the means equal to each other? Or the null hypothesis suggests that they are equal, and the alternative hypothesis suggests that they're different. Then you perform your um, test statistic, which is given by this. It's very similar to your expression for the confidence interval. and then the p-value is exactly equal to this. Right? So it's 2 times the probability that t is greater than your observed value for t. And this big T is follows a T, and then you get a p-value here, which is equal to this. And then therefore, what you can do is you just compute your actual probability. To do this, you just compute T inverse, and then that will give you the expression that you want. And the final thing is, well, you know that p equals to 0.0036, so we reject H0, we reject the null hypothesis if the probability that, or the p-value that you get is less. And this basically concludes the end of the drop-offs. My internet is not behaving well today for some reason. But hopefully this seminar has been helpful. These slides will be released hopefully fairly soon as well.